Recording it's rolling. It is Tuesday, April 14th. You gotta talk about the sign up with you guys. Okay, and then there's this exciting senior takeover opportunity to talk about. Tomorrow I want to do a lab with you guys that involves this Play-Doh. So I'll do a preview with you guys today. Okay, it has to do with a property called resistivity. Like what's the resistance in a copper wire versus aluminum wire versus maybe a Play-Doh wire. Okay. And then last few days we've been looking at this page, and you guys had here we go. This lab page to go along with it. Now I think most of you guys finished the lab. Actually, a couple of you guys finished this already, but if you hadn't yet, then I do want to at least go over this one here with you guys and give you guys some more class time, maybe a few minutes in the class. So back to the beginning here. Science elective for next year, sign up. Okay, so I'm going to pass this paper around in a few minutes, but right before I hand that to you guys, I want you guys to see what your teachers are seeing. So all your teachers received an email, or as far as I know, received an email with a link. It looks like this. Okay, and then do you guys see at the bottom there's these different tabs? You guys see different tabs down here? Okay, so let's call this the science class, and then I scroll down to where I found you guys. All right, so here's you guys right here. Okay, so I'm highlighting. Okay, you guys are all right here. All right here. Your name's somewhere right here. Okay. Okay, so I get to choose in this drop-down box one of these options. Right. So guys, look here so you know what these options are. AP Physics 1 is the AP Physics class that I teach, actually what I designed all these posters for. So if you want basically this class, minus all this electricity stuff, and at a harder level, like in an AP level. Now, the difference between this red and this green here, you guys see this green says AP Physics C and then M. Does anybody know what the M stands for? Yeah, mechanics. Yeah, it stands for mechanics. Actually, this green class and this red class are fairly similar, except that this green class is a little harder and it involves calculus. Also, Mr. Gentili teaches it, so hey, you get a different perspective too. So if you want a pretty solid AP class that's, again, fairly similar to this honors class, that's more conceptual type and algebra based, that's this red one. And then if you want the calculus version, that's a little harder, then that would be that green one. Then, if you want some other AP class that's not physics, then there's an option for that. Now, if I check this box for you, then I'm sure your counselor will pull you down and say, okay, well, which AP class do you want to take? Because I know we got what biology, chemistry, environmental, at least, right? Would be. Great. Yeah, am I missing any? I think those. Okay. Or if you're like, hey, maybe I don't want to do an AP at all. Maybe I just want to do like a regular like honors class or something. You do honors. Okay. And so those are your main options right there. If you have a none of the above, something going on a little bit different, then you can write a note, and I will be able to figure out what to do from there. Okay, so I got these options here. So I'm going to pass this page around. You can write your name. So I'll give you guys an example here. Name. And let's say maybe you want to take my AP Physics class. Right? Okay, that could be option 2. If you just write it 2, then I'll know how to match that and do it. Right? And if you have something special going on, you can just write in the spot. Okay. All right, so got some rows here, got back. All right, so pass this around, and at some point, get your hands on that, write your name, and what you want to do. All right, next thing, there's something new, looks like from admin called Senior Takeover Day. On this special day, seniors will have the opportunity to take over the role of a faculty member, engage in way to experience leadership and gain insight into responsibilities of school staff. Okay, now, this is actually a permission slip. Okay, so if you were interested, you could fill this out. Oh, I forgot to tell you the date. It's Friday the 24th. So Friday, April 24th, 10 days from now, Friday the 24th. Okay. I'll print some more of these out in case you're interested. But I think on this next couple of days if you are, so that I can turn this into the office. I don't know why they want permission slips. Maybe they want to keep a record or give you guys volunteer hours. Maybe I don't know. I don't want to promise something they're not doing. But if you were interested in this class, if you want to teach the class on that day, okay, come around with that. So let me know if you want to teach the class, or maybe a few of you guys want to teach the class that day. And if somebody's interested, then yeah, we'll plan on that. Yeah, if you're a junior, I'll let you do this class. I mean, I don't know if they would do whatever on their side for, but yeah. All right. Yeah, if you're a junior, that's okay for this class. Do that. All right. So, any questions so far? Schedules, senior takeover day. All right. All right. Let's actually, I want to lead into this with, I got a PowerPoint ready, and let's go down this PowerPoint here. Okay. So we're gonna do a little bit of a review, some concepts you guys have seen. and then I'll eventually run into that lab we're doing tomorrow. So, guys, if you have three resistors in series, you guys seen this one? What would the waterfall model look like? Is it just a one-way street? Yeah, there's only one path for the electricity to flow or the water to flow. So, right, this will be looking like that. All right, guys, let's do a Kirchhoff table. Suppose I have a 12-volt battery. Guys, you have a 12-volt battery, and I have resistors that are 1, 2, and 3 ohms. Okay. Guys, what's the total equivalent resistance for that whole circuit? Yeah, it's got to be 6 because you can very simply add those up because they're all in series. All right, next, let's do Ohm's law with the point of value. There's lots of different ways you can complete this table in different orders. I'm just looking at my PowerPoint screen. This number's going to pop up. Okay, how many amps are supplied by the battery? Can you do Ohm's law with the point of the battery? You see Ohm's law in front of me? So I equals what over what?
Voltage over resistance.
Yeah, V over R. And 12 divided by 6 is 2. So it's going to be 2 amps. So 2 amps are leaving the battery. You see that? That's the current supplied by the battery. Oh, you know what? Guys, if 2 amps leave the battery, what's the current through this resistor? 2 amps. How about this one? 2 amps. How about this one? 2 amps. Because they're all in series. So isn't that entire column have to be 2? Right? Yeah, because they're all in series. Right? Oh, well, now that you have each resistance, which was given, and also each current, can you find out the rest of the voltages? Now we can use Ohm's law in a different way. So voltage can be equal to what times what?
Resistance times amp.
Yeah, so I times R. So 1 times 2 is 2. 2 times 2 is 4. 2 times 3 is 6. Aha. Okay. Finally, can you use Joule's law to calculate the power in watts? Okay. And one version is power is current times voltage. So could I do I times V? So 2 times 2 is 4 watts. 2 times 4 is 8 watts. 2 times 12 is 12 watts. Okay. Hey guys, this last cell, could I do 2 times 12 and get 24 watts supplied by the battery? But let's do the other check. Does supply match demand? So how much power total is demanded by my resistors? Add them all up. Do I get 24 watts there? 24 watts supplied by the battery. It's a match. Okay. All right, how about 3 in parallel? Did I do this one with guys yesterday, I think? Do this one? Right. It's a parallel. All right, so the current splits 3 ways. Right? But notice that voltage is the same on all of them. Okay, because they're all in parallel. Right? So again, 3 resistors are given. The battery is given. I got 12 volts going again. Hey, Paul, if you had a 12 volt battery. Oh, I forgot to ask guys. Guys, could you do, there are different ways to solve this. I could do 1 over 2 plus 1 over 3 plus 1 over 6, and then take that reciprocal, right? Because if it took you 2 hours to paint a fence, and you get 2 of your slow friends, 3 hours and 6 hours, collectively, you would be finishing the job faster than you could yourself. And okay, you guys see here, if you do the math, it comes out to 1 hour. Okay? All right, so here, I'll show you guys the rest of the numbers. So 12 over 1 is 12. Right. The voltage drop is 12 volts on all these. Think of you Ohm's law to figure out the current. Right. Guys, notice the current is different because the current splits and the resistors are different. So, guys, where does more current go? Does more current go through the larger resistor or the smaller resistor? More. Which one is the most current going through? Yeah, resistor A, which is the smallest resistor. Do you guys see that? You guys see that inverse relationship? The less the resistance, the more the current. Right? I think that makes sense, right? If I'm driving around town and I see different streets I can drive on. One has a bunch of stoplights. I'm probably not going to take that road, right? And then you can use Joule's law, just like we did before, to get the power in watts and do the check and all that stuff. All right, here's a hybrid scenario. You get a little bit of it. Huh? Oh yeah, back to. Oh yeah. So the number's a little different. All right, we got a hybrid scenario. We got a mix. There's some parallel, some series going on. All right. All right. So these are. I'll do a process question with you guys today that looks close to it. All right, where it's a little hybrid. Okay. All right, so you can figure these out. Did I tell you guys I uploaded this whole presentation I'm going through right now? I did upload this to Google Classroom a few weeks ago. Right. All the animations. It's just animations and thumbnails. Okay. Okay. Oh, and I got a real fancy one going on here. Okay, real fancy. You want a real tough one? Okay. All right, circuit. Oh, I forgot I had this slide. Yeah, let's do this one. You guys know that's battery voltage. You guys know the long side represents the positive terminal. How about Some of these I have told you, and some of these I have not. Guys, what do you think this is? Uh, It's called a fuse. So if you ever overload the circuit, there's too much current flowing, then that'll break the fuse and it'll stop the current. It's a safety feature. Oh, this one you guys have seen. What's this?
Wait, wait.
Yeah, it's a switch. Yeah, like an on-off switch. You guys saw the flashlight schematic. Well, what's this one?
This is it.
Yeah, there's your classic resistor. I don't think I told you these two.
That.
Yeah, it's a capacitor and an inductor. I might talk about this next week. Okay, right. Don't worry about this so much right now. Oh, do you guys remember how to connect a voltmeter and an ammeter? You guys have been using these last few days. So this voltmeter is connected in what? Series or parallel? Huh? We're looking for a voltage drop, a difference in voltage. Versus, I definitely see the ammeters connected differently. Do you see how you have to break open the circuit to force the current to flow through the ammeter? Which is different. So
Little box.
yeah. That multimeter, that little orange box you got to work with. Exactly. Yeah, here's the voltmeter aspect, and if you switch the toggle switch, then here's the ammeter aspect. So is this series or parallel up here?
Parallel.
Yeah, parallel. Oh, okay, then series down here. Yeah. Right, that's how you measure your voltage and correct. Okay, guys, here's tomorrow's lab. So suppose you have some wire, and I zoom way in on it, like microscopic. And okay, so now it looks like a cylinder. You guys see a cylinder? I'll have you guys make it into a cylinder. Okay. Um, can you guys imagine that maybe a copper wire versus aluminum wire would transmit electricity differently? Like maybe one's like more efficient, one heats up more or something like that. Okay, so that property is called resistivity. And we can put together an equation here. It goes like this. So the resistance from end to end, especially if you have a wire that's like a mile long, if you have a little short wire, it's like size of a paperclip, it's hardly any resistance. But if you have a wire that's like a mile long or 5 miles long, then from end to end, the total resistance is proportional to the length. So if it's twice as long, it's twice the resistance. Right? Guys, what about this cross-sectional area? Like, guys, a skinny wire and a fat wire. Which do you think has more resistance, a skinny wire or a fat wire?
Yeah.
Well, that's a different question. If you which do you think would be more difficult to draw water through a straw? A little skinny straw, like maybe one of those little stir straws, or a big wide straw? Which one is more difficult to draw water through? I think a little skinny straw, a little stir straw, right? A little skinny one. It's hard to draw any water through that. Right? So how about the wire? Is it easy? Switch up easier, more difficult. Anyway, guys, the fatter the wire, the less resistance. The skinnier the wire, the more the resistance. That's why, guys, look at this formula. I want you guys to really make sense of this. Right? Is how to interpret formulas like this. Because when you graduate high school and blah, 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 right, you're going to forget a lot of these technical details. But what I want you guys to remember from high school is like, okay, I know how to interpret an equation. I know the relationships among things. See if I'm dividing by cross-sectional area to get the resistance? Right. So the larger the resistance, or sorry, the larger the area, the less the resistance, and vice versa. There's an inverse relationship. Okay. Right, but what ties it all together makes the exact equation is this resistivity. And that is a material property. And okay, which is turns out the slope of that graph right there. And tomorrow you guys are gonna get a lab paper that looks pretty much like that. Okay. So show you guys a bit over here. I got what I need. All right, so I'm gonna build this from scratch. Got some Play-Doh. Play-Doh here. Okay, I'm gonna make a dough cylinder out of this. Okay. Yeah, this looks good. It looks kind of like a wire. Okay. Hook up my battery. Um, got a multimeter. Okay. Now this is a lab that sort of barely works, but it does work and it gives accurate numbers. That you can Google the answer. What's the resistivity of this Play-Doh material? Okay. What do you think is more conductive, copper or Play-Doh? Yeah, copper is definitely more conductive. Okay, so I think the resistivity value on this Play-Doh would be more than copper. Okay, so how can we find that? I did want to show you guys that there is a current going through this. So if I put this up here, all right. So see, this is like sorry. Let's see. Oh, there it is. Okay. Here, you guys see this little LED? This little LED. Right. Now there, these two wires. Um, the long wire you want to attach to the positive end because the electricity only flows one way. Right? The crystal side you can switch either way, it didn't matter. Okay. But watch this. Whoops. So I gotta separate. I just turned it on. Gotta go reset this. All right. There you go. Got that set up. And hey, you were just turning on. Did I switch it? Oh, I got that backwards. That was it. Okay. Okay. You guys see how that turns on right there? I see it turn on. Okay. Okay. So this Play-Doh is definitely conducting electricity. I have a circuit there. I have a whole circuit. Okay. Now just to remind you guys, if I take this LED, if I take it out and I switch it around 180 degrees, is it going to turn on anymore? No, because the electricity only flows one way through an LED. All right, there you go. Only one way through. Is that? Oh yeah.
Where do you connect the ends of the Play-Doh so it's a half or?
Oh, connect these ends.
Yeah.
Let's see what happens. Let's see. Yes, the LED does stay on, and I think the reason is because this would be the path of least resistance. Like the electricity is thinking like, I could go through here. There's hardly any resistance. Or I could go through, like through these 100 stoplights. Yeah, I'd rather just go across the LED.
Oh.
Yeah. So that's path of least resistance. Okay. Now what if I connect them like down here? That might not be the case anymore. Let's see. Oh no, it still stays on. I thought it was going to turn off. Okay. I guess it still turns on.
But if I get a big ball, like a Play-Doh, stick a bunch of lights in it.
Huh?
If you get like a big ball Play-Doh at the top, you just stick a bunch of lights in it.
Well, see, this LED is being a bridge. You guys see how the LED is a bridge between the left side and the right side? Right. So, like, if I put it over here, is it going to turn on? No. Or same thing over here, it doesn't turn on. Right. So I really have to bridge the left side and the right side. Did that? Right there. Oh, I just saw it. It was off. There it is. It's extremely dim right there. It's extremely dim. When I separate this, now the current's forced to flow through the LED. Okay. Okay. So yeah, so this Play-Doh is conductive, but how conductive? So I got my multimeter. Let me try voltage first. So pop this in. The voltage side, got voltage right here. I turns the voltage, and well, I got to measure the potential difference from let's say here to here. Let's see what I'm getting. All right, I'm getting 5.7 volts. Is that? I know I have a 9 volt battery. I was really looking for more like 9 volts, but this showed up in the lab for you guys too the last few days. For some reason, I don't know why you hooked this up. It drops a few volts. Anyway, I got about 5.8 volts, something like that. Okay, now what's the current? So I'm going to make some changes, just like you guys did last few days. Okay, switch this over here. Boink. Switch this to I think that one right there is what I want. Okay. Now I need to break open the circuit and force the current to flow through the multimeter. Okay. Oh, you know what? Too. I'm just gonna. Well, I'll leave the LED there. I don't know if I'm gonna get anything yet, but let's try. Okay. Is this actually gonna show anything? Oh, well, there is a current going through. Let's see. Let me try this. Aha! Okay, I'm barely getting a number. You guys see it's 0.01 amps? You guys see that 0.01 amps? Right. That's what I'm saying, like in past years, I've seen this lab like barely works because normally by the time you get to this step in particular, it barely shows up. So I'm looking at I'll just call it 0.01 amps. You guys see that? Okay. Hey guys, if you know the current, which I just found, you know the voltage, which I got before, then is there enough information you could calculate the resistance in that circuit?
Yeah.
Resistance. Okay. And then if you know the length of this dose cylinder, actually I should have said it this way. I'll show you guys. Okay. If you know the length that the current has to pass through, and you can determine the cross-sectional area, then all the information is there that you can eventually use that formula I just showed you guys on the PowerPoint to calculate what is the resistivity of the dough. Right. Okay, so I'll do that tomorrow also, but not here. Now let's see if this is set. Okay, still set the current. Let's see current flow here. Yeah, it's still. Even better. Guys, now I'm actually getting a better number. Is that it's like 0.03? Okay. Okay, so I took the LED out. Okay. Okay. But the current's passing through all through this length. So this length is probably some number of centimeters. Okay. So I could say from here to here, it's looks like about 11 centimeters or so. Okay. And then I can go get the diameter of this thing. It looks like the diameter is about 1.5 centimeters. If you know the diameter, can you calculate the cross-sectional area if it's a circle? Right? You guys do that? Okay. So that'll be tomorrow's adventure. All right. So you guys ready for Play-Doh tomorrow? So this aside, so I do want to cover with you guys at least this one and maybe one for the other side, and then give you guys the rest of the class to work on these. Okay, so okay. Oh, you know what? Let me see if I got a different version too. Yeah, this one here. Just so if you have the same version I did. Okay. Um. Yeah. I think so. Yeah, I think I'll probably do that. Yeah. Oh. Yeah. Let you guys. Put it all right. So let's do. Pop this up a bit here. Okay. Because I think number two is probably the most difficult one on this page. Okay. And so I gave you all of the resistances and ohms, so you know all the resistors, and I gave you the battery. My battery is 24 volts. So first thing we got to figure out is what's the total equivalent resistance of the entire circuit. And the way you're going to do that is, here, maybe I'll label my resistors. Got A and B is, this is 6 and 6. C and D are 1 and 2. These are all ohms. And resistor E is 3 ohms. Okay, so that's labeled. Okay. You guys remember the process? Find my voltage source, fly over to the opposite side, work my way back towards the source, and find equivalent resistances. You guys, what's 6 and 6 in parallel?
Well,
If it takes you 6 hours to paint a fence and your friend 6 hours and you work together, how long does it take? Three. Guys, that's basically a 3 ohm resistor right there, isn't it? So this is 3. That's 3 ohms. Now let's go back. So, now this, and this would be in what with each other? Series or parallel? Series. So we have 1 ohm, 3 ohms, 2 ohms. Guess what is 1 plus 3 plus 2?
9.
What? 1 plus 3 plus 2?
Oh, I thought you were talking about the 6 others. 6.
Yeah, 6. This one, these are collectively 3, and this is 2. Yeah, so that's 6 ohms. So all this branch is basically 6 ohms. Right. Now let's go back. That's in what series or parallel with this last one? Parallel. This last one says 3 ohms. So let's do 6 and 3 in parallel. Can we just do product over sum? Is that okay? 6 times 3 over 6 plus 3. I'm getting 2 ohms. Is that okay? 2 ohms? Right? Did I tell you guys all the numbers on this page should be what? Whole numbers or decimals?
Oh.
Yeah, yes, you should only get whole numbers on this page. Well, on this side anyway. Oh, I forgot to draw my waterfall. Let's draw a little waterfall here. Looks like resistor E is going to drop all the way down, route back. Then we go across D here. Then it splits to A and B. So here's split A and B. Then it recombines to go through resistor C. And then combines back and back to the top. Okay, so there's your waterfall model. Voltage drop. Actually, based on that picture I just drew, guys, what's the voltage drop across this one right here? It's the same as the battery. Same as the battery. So that would be 24 volts. EDCVA. Okay. Okay. Now here's where things get a little tricky, and there's different ways you can solve this. But I'm going to draw one of those equivalent circuits that we had along the way. Let's do this. So I got my 24 volts right here. This is 3 ohms right here. This is 2 ohms, 1 ohm. Okay. But remember the 6 and 6 in parallel way over here is kind of like 3 ohms. Okay, just a single 3 ohm. Right. So this is one of my equivalent circuits. Now, I know 24 volts drop from this point to this point because that's across that one. We just said that. Okay. Does that mean if I follow the branch, like the other branch, go the other way, it's also collectively drops 24 volts? Is that right? 24 volts. Okay. Now here's where I'm going to break open Kirchhoff's rules. We're going to use one that, well, we looked at, but hadn't really tried out class yet. Guys, this one right here. It says the voltage drop, if you have a bunch of resistors in series like this, is just very simply proportional to the resistor. Okay. Yeah, I can add a resistor C down here, and that's what I'm going to do. So I have 24 volts drop from here to here. And I'm going to say times, let's say 2 over, guys, what's 2 plus 3 plus 1? 6. Oh, 2 over 6, is that like a third? What's a third of 24?
8.
8 volts. So 8 volts drop across this 2 ohm resistor. 8 volts. Right. I bet I could grab this 1 ohm resistor here. Let's do 24 volts times 1/6. What is that? Yeah, 4 volts. 4 volts. Okay. Now that was resistor C. Oh, okay, yeah, that is this one right here. Okay. Now A and B. Oh, remember how A and B were parallel to each other? Does that mean they have to have the same voltage drop?
Yeah.
Okay. And actually, let's solve this one a little bit different. Because if 24 volts drop total, actually, you probably do this way anyway. Okay. Guys, what is 3/6? Is that half?
Yeah.
What's half of 24? Would be 12. Okay. But another way I want you guys to see this, and that accounts for each of those, okay, is if you add these three up, is what's 8 plus 4 plus 12?
24.
Also 24. So it's like you restored the height of the original cliff. You guys see that? Okay, so that's also called Kirchhoff's loop rule. Now I don't have to double count this 12 because I have two side by side waterfalls, so I will only count one of these and not both of them to add up the total height. You guys see that? Okay. All right. So now we got those.
Put that back.
Yeah.
Yeah.
We got that.
All right, thank you.
Yeah. Oh, I think we can use Ohm's law and Joule's law to finish the rest of the table. A little plug and chug here. So I equals V over R, 24 over 3, 8, 8 over 2, 4, 4 over 1, 4, 12 over 6, 2, 12 over 6, 2. 24 over 12, or sorry, 24 over 2 is 12. So I just did Ohm's law. I said I equals V over R. Okay. Now I can switch over to Joule's law. Power is current times voltage is one way to do that. Okay, some kind of big numbers here. So 24 times 8 is 192 watts. 8 times 4 is 32 watts. 16 watts. 24 watts. 24 watts. Okay. Now this last one was 24 times 12 is 288 watts. Should this be 288 watts? Okay. Now let's check supply and demand. What's 90, 192, 32, 16, 24, and 24? Yep, it's the same thing. I mean, of course, it's going to be 288 watts. Okay. Right, you guys got that? That's good. You know what I did forgetting to point out on this page? You guys see this little note here says circle the brightest bulb? Guys, what metric do you think would indicate the brightest bulb?
At least
No,
most.
Okay, I think you're kind of onto something. Guys, do you think if it has a smaller resistance? Hold on. Yeah, because power could also be B squared over R. Yeah, because it has a smaller resistance. I think that would tend to draw more power. That is true, but that's not the only thing. So there's actually another metric I really want to hone in on. Okay, because it's not just the resistance. Isn't it also how much voltage is going through it and how much current? Put it all together, you can get power. Do you guys think it should be the greatest power? The greatest power? Yeah. So guys, which one of these has the greatest power going through it?
E.
Yeah, I'm looking at this one right here. Oh, okay, so resistor E, so I could circle that one. Okay. Oh, guys, that's not true on your lab when you were hooking up all these Christmas lights. If you had one that was in parallel with a bunch in series, the one that was in parallel like this glowed really bright, and the other ones were fairly dim. Yeah. So that would definitely be the brightest bulb, wouldn't it? Yeah. Okay. All right, guys, good. Good. All right, now other side here. How about let's do a 1314. Let's do this one right here. 1314. Okay. All right, so I'm gonna draw that on paper and make that look bigger. So number 13 and 14. So okay, copy my numbers here. Got 4 ohms, 6 ohms, 8 ohms, or 7 ohms, 5 is 3 ohms. Or no, that's not right. That's 5. 5 ohms there. And then this guy's 3 ohms. Okay. Okay, so that's my circuit copy. Oh, and then these are all 5 volt batteries. Okay, so equivalent resistance. What's these three in series add up to what?
What? No. That's 8, so 21.
Yeah, 21. 21 ohms. Right there, 21. Okay. Now bring it back to this guy, which is 3 ohms. Oh, so 3 and 21. Is that series or parallel? Parallel. Okay, 21 times 3 over 21 plus 3. Yeah, let's see what is that. 21 times 3 over 20. I'm looking at 2.625. That's supposed to be ohms. So ohms. Okay. All right, so now I'm going to redraw the circuit again. 2.625 ohms. This guy's 5 ohms. This guy's 4 ohms. And battery 5 volts. Okay. Oh, we're almost up finish. Because those are all in what with each other? Series. Can I just add them up? 5, 4 is 9, 10, 11. I think it goes to be 11.6 ohms. Should that be the total resistance? Okay. Okay. All right, let's see. Is that an answer choice? Yep. I see that as an answer choice right there. 11.6 ohms. Okay. Now that we got that, the follow-up question is what's the current supplied by the battery? Does it sound like Ohm's law? Ohm's law. We're doing V over R. Okay. I equals V over R. Okay. So let's take 5 volts, put it on 11.6 ohms. That should tell me how much current is flowing. We got 0.43 amps, which is an answer choice. All right. All right, so you guys good on that? All right. Yeah, we got a solid 15 minutes left in class, so make good use of your time to either solve that page or a couple of guys need multimeters to finish a little bit of lab, so I'll get that to you guys too. All right, put the guys out here.